Hi, everybody. I'm Patrick, and as I think I demonstrated a little while ago, I'm not the technical brains behind this operation. So I'm going to try and keep my presentation fairly quick and let Ron get into the nitty-gritty of some of the analysis that we've been doing to try to build hierarchy in the data that is presented to users in the OPAC. Classification and hierarchy are fundamental human impulses, and I just want to give some broader context to some of the work we've been doing. This is Robert Flood's great chain of being, which he produced in 1617. And this idea has had variations throughout the Western ideology since the time of classical Greece, right through the Enlightenment. This image just serves to remind us that as good as one classification scheme may be, there are other worldviews that also have their place. Linnaeus's monumental taxonomy of life on Earth took a more empirical view. Though even some of Linnaeus's work was not without some ideological baggage that is unpalatable. So whether we look at Linnaeus, the great chain of being, or the allocation of real estate in Dewey and LCC, I would suggest that any classification system is a cultural construction. And the point is that there does not just have to be one schema. And facets are actually a great way to allow different worldviews to coexist when looking at the same universe. Moving on now from the cosmos to the shopping mall. Retailing is one setting in which faceting has really been put through its paces. And it's a good illustration for anyone who's not clear on how facets work. The headings on the left allow me to view and filter the same universe using different organizational schemas. In the library OPAC, there are many uses for hierarchical facets. They're appropriate in any situation, basically, where you have too much data to easily process or navigate by a person. Machines are very good at that kind of thing. People are not. And today we're going to focus on the use of hierarchies in search results. Why do we need facets in search? I can think of three reasons, and there are probably more. Search result sets are a lot bigger today than they were in the past for several reasons, and I'll say more about that in a minute. More metadata is associated with each result now as we pull in data from various sources and web services. And I think the main reason, again, comes back to the human being and the human brain, and that is that we just can't manage large lists of data. One reason that the result sets are a lot bigger is sort of a change in paradigms for entering queries. There are two paradigms, I think, and this is perhaps an older one, where you choose your facets before as you enter your search query. You can choose to enter them beforehand or not, and I think this is the web model for search, which is sort of the emerging paradigm, and it seems to have taken a pretty strong hold in the library world as well, where you'll often find the single box keyword search is the norm. The truth is that even with a small result set, facets can quickly become overwhelming, and I think there are a lot of different dimensions on which one can choose to facet. I've just listed a few of them here. I'm just going to skip ahead a bit here because I'm worried I'm running out of time. I want to just mention briefly the FAST model, which is an interesting one. It looks at LCSH. It's some research that's been come out of OCLC, and it takes LCSH and tries to strip away some facets from that data, including form, chronological information, etc. And I think it's an interesting model. It's problematic when you actually strip that information away from the subject heading string, because the data itself loses its context, as does what you leave behind. But I think it is interesting if you were able to pull that information away and facet on it, but still leave the strings intact. One other problem, though, is that it still leaves this sort of hard nut of subject information, topical information behind, which and the LCSH data is really relational. It's got hierarchy, but it's not it's got relationships, but it's not necessarily hierarchy. And I think some people recently have done some nice illustrations of the absurd results that you can get if you try to view LCSH as a hierarchy. It just doesn't make sense beyond a few links. There are some great projects, and I'm not going to linger long on subject headings because I want to get to user-generated tagging as sort of an alternative worldview. Certainly, it brings with it a new vocabulary, and which is useful because that's the vocabulary of our users. It also possibly brings new conceptualizations and arrangements of information. But I just want to mention this project at Columbia University. Some of you may be aware of it. They actually use the LCC classification to build a browsing interface for their electronic resources. And I put this slide up because I think you can see it actually they actually reconfigured one of the more problematic areas of the real estate allocation in LCC. Flat tag sets are a problem, and we've been experimenting with ways to build hierarchy in tags themselves. And one way of doing that is to build structure in the interface in which tags are actually collected. And in this example, we used labels associated with three or four tag elements, and the results were actually quite interesting. We were able to encourage people. It's kind of like pre-coordination. You're associating a label with a subsequent term, and we found it produced quite interesting results, and allowed already a kind of grouping. And you can see that the mood style label evoked adjectives which is actually kind of a tag that is not frequently seen in tag sets. So that's a beginning at starting to create some structure, and which is breaking down a large body of data and making it more navigable and digestible by a user. So I'm going to pass the microphone over to Ron now, and he can tell you a little bit more about some of the analysis that we've done on this kind of flat body of user-generated tag data.
Okay, cool. So I apologize up front. I'm going to talk really fast, cover a lot of ground, just throw it all at you, and hopefully some of it will stick or pique your interest. I'm going to give you a bunch of references at the very end, which will cover all this in greater detail, make sense of what I'm talking about here. Okay, so we have a big set of user-generated tags, something like Delicious provides. How can we bring structure to that? Modeling tags as instances of these tuples where an individual user has assigned a tag to a particular bib, right, a particular item in a library. So if you're going to cluster this to start separating out some of the structuring data, things that make tags like other tags, you can use clustering techniques. These are mostly from machine learning, natural language processing communities. They're starting to get applied to this task. The idea is very simple. Come up with a similarity measure between tags and then start clustering. So take your first tag, seed a cluster with it, take your second, compare it to that cluster. If it's close enough according to this similarity measure, I'll give you an example of such a measure in a moment, then add it to the cluster, otherwise seed a new cluster. Continue until you've sort of partitioned all of your tags into clusters. Obviously, I'm glossing over a lot of complexities. How do you choose your similarity measure? How do you do cluster normalization when you're comparing a tag to a cluster? Do you compare it to all tags in that cluster or a centroid representation, whatever? Can a tag sit in multiple clusters? Probably, because there's a lot of polysemy in tags, ambiguity. They can mean many things, so they probably cluster in many locations. So it's an example of similarity. I'll touch on the slide briefly. It probably won't make sense, but hopefully you'll get something from it. There's a similarity metric called vector cosine similarity. It works like this. For each tag, we're going to model it as a vector of weighted features. The features are the bibs that the tag has been assigned to. So your space of all features are all of the bibs that this tag has been assigned to by some users. That's the full space. The weights on those features are the number of times across all users that a tag has been assigned. So again, don't worry about the details. You're constructing a vector of these sort of bibs, and this bib has been assigned this tag this number of times by users. Then you can apply this magic formula down here on the fourth bullet. Take the cross product of these two vectors, divide it by the Euclidean distance. Maybe this means something to someone. What you should take away, what this is doing, is it's looking for overlap between the bibs that each of the tags have been applied to. So if a lot of bibs receive the same two tags, then the similarity metric will be high. There's actually a physical interpretation for this. We're measuring the cosine of the angular distance between vectors. So I have this vector representation based on the bibs that this tag has been assigned to. I have another vector for another tag. If there's a lot of overlap between the bibs, the angular distance is close. Take the cosine, you get close to similarity of 1. If they're completely orthogonal, they share no bibs, all of the tags have been assigned to completely different bibs, then you have a 90-degree angle, you have 0 similarity. So there's some physical underpinning to all this. Just get the idea that you're measuring overlap in bibs that tags have been assigned to. Okay, here's an example of a cluster. We ran an experiment with about 1,000 tags, probably a couple hundred bibs, and here's one of the clusters that emerged. If you look at it, you can probably guess one of the titles that was tagged: Leonardo da Vinci, Opus Dei, etc. Thank you, Mr. Braun. So this is kind of flat. You get a bunch of these clusters. Can we start structuring this? How would you go about that? Well, let's look first what kind of relationships exist within a cluster. There are unifications, right? Different people tag items using different terminology, but they're talking about the same concepts. Simple examples of this are misspellings, maybe British versus American spellings. Someone actually misspells something, you tag it TV, I tag it television. These are all sort of unified concepts and could be conflated in some sense. There are also abstraction relationships where different users use different levels of generality. Let's say you care about dogs and you read a book about dog. You might tag it with something like German Shepherd or Collie. I don't care about dogs. I just slap the tag dog on there. Right? Across users, there are going to be some differences in generality between the tags that are used. So it's these kind of abstraction relationships that we're interested in getting at to support this hierarchical faceting. So presenting this to the user, I'd like to show the user dog and let them drill down if they care about the individual dogs. If they don't care about, they can click on dog and get all the space of bibs that were tagged with dog or any of its subsets. So you can do that kind of a hierarchical abstraction navigation if you can recover some of this data from your tag sets. Also, you can get semantic relationships, these various associations where just tags tend to co-occur because they're related by bibs. For example, you might tag something with car, I tag it with engine. There's a relationship because cars have engines, so across bibs, this type of associations might tend to occur. Why do you care about these? Well, if you think about linkages where you're doing see also links, you might want to point users to related semantic concepts that are co-occurring with some of your tags. Also, there is another type of stuff that occurs in cluster. It's just spurious associations, right? Noise, we call it crap. You get used to it. It's machine learning techniques come out with this stuff. Okay, so we have those types of relationships. Can we get at some of them, particularly the abstraction relationships? Here's some methods. I break these into two classes. I call them intrinsic or extrinsic. Intrinsic are data-driven techniques. They're coming from the data, bottom up. You're building structure purely from the data. Extrinsic methods are taking external resources and using the relationships in those resources. You map your tags into those resources, use the resource relationships to structure your tags. All right, so let's talk about some simple intrinsic methods. Obviously, lexical subsumption is an example. If a tag is completely lexically contained in another tag, that other tag is probably a refinement of the original tag. For example, picture book contains book, so picture book is probably a refinement of book. Similarly, children's picture book is a specialization of picture book. Not that useful in practice, but it does some stuff for you. You can also look at operational definitions of subsumption. If a tag covers this set of bibs, it's been applied to this set of bibs, and I have a second tag that also is applied to the same set of bibs, and then a bunch more, then that second tag is probably more general than the first because it has broader coverage. So you can sort of operationalize that definition by looking at overlap of coverage between tags. Usually, to say something subsumes for another, you don't require complete coverage. You have an operational definition like it needs to cover about 80% of the same bibs. And again, the subsumption relationship is just an abstraction relationship. You can also use a sort of an old workhorse from knowledge discovery or KDD community called association rules to characterize the association strengths between any two arbitrary tags. Plenty of tools out there that will do this for you. What's nice about it is they come up with support and confidence metrics that let you start really evaluating the strengths of similarity between tags and start to carve up those different relationship classes a little bit. It's also very nice to have confidence relationships because you can direct user attention to clean up some of this stuff where the model thinks that its performance is weakest. Most interesting, probably, I think, is using social network theory. So how would this work? So let's build a similarity graph. What do we do? Build a graph. Every tag is a vertex in this graph. We're going to connect two vertices or two tags if they meet some similarity threshold. If that happens, connect them. You have this huge connected graph at the end of that. Let's go and apply network theory to, for example, compute closeness centrality for all of the nodes in this graph. Right? More central a node is, the shorter its path to all other nodes in a graph. If you think of any taxonomy, the topmost node is very central. It's very general. It has the shortest paths to all things indexed under it. Right? So the heuristic that we're going to use is the greater the closeness centrality, the more likely the tag is to be a general tag. So when we go back and do our clustering, we're going to first order all of our tags by this closeness centrality method with the highest values first. So we're going to insert into our clusters the most general tags first. And then as we get to more specific tags, if this heuristic is working, we'll start indexing those beneath the more general concepts. So looking at an example, our previous example, here's some of the structure that falls out. This algorithm is described in Heyman Garcia Molina. It'll be in this group of references that I give you. So you see some structure here, right? This first cluster, I would probably move family tree down and maybe relabel this first sub-cluster something like, the world according to Dan Braun, or how to make a buck, something like that. This second one, atheism, obviously is related to Christianity. But the data is really telling us interesting things about what those relationships are. There are probably a bunch of tagged intelligent design texts, right? They're telling you that there's potentially some opposition or some relationship between atheism and Christianity. This notion that Darwinism is somehow atheistic. So you can start seeing some of this stuff fall out of the data as you do this. Again, Christian ethics actually fits pretty well beneath Christianity. Again, remember, Christianity is the most central concept, meaning it's the most abstract, and so it's sitting pretty properly at the top of the tree there. Bible stories and morality tales are sort of two modalities for expressing Christian ethics. So as a human, I can look at this, see some of the structure, and maybe clean it up a little bit, do some curation before it's actually presented or before it's being used operationally. Looking very briefly at extrinsic methods, because I'm almost out of time. One is to use a resource like WordNet, which provides the senses of words in English. It also provides an abstraction hierarchy. And if you can map your tags into that WordNet resource, then you can use those structures to in turn structure your tags. Marty Hurst over at Berkeley has done some interesting work on Castanet, I think, Flamenco project, doing just this. You might also be able to use Library of Congress classifications. Again, you have to do this mapping, though, from your tags into these ontologies. It's a classification task. It's error-prone. Can you do it well enough to be of use to your users? It's an empirical question. You have to run the experiment, see if it's useful or not. Also, as soon as you start having specialized ontologies like geospatial, there's lots of resources out there. This mood tag that Patrick showed you earlier, we want to look at some work in the sentiment AI community. They're starting to characterize gazetteers that describe sentiment for doing opinion analysis and so forth. So maybe we can get some pointers about how to structure that mood tag. Okay, so I'm so close. I'm just going to summarize. You don't have to just analyze tags using this methodology. I can also represent users as feature vectors of the tags that they use, and then do the same sort of similarity measurement to find users who are very close to each other, to identify affinity groups. Similarly, I can take two bib titles, look at their overlapping tag, and get a measure of how similar these titles are. So this methodology really provides a strong formal statistical framework for analyzing all of these relationships in the data. Last slide. Can this do everything for you, these automated methods? You know, can you generate your own DOI system? No. They're very sensitive to the data that is visible to them. They're very good for solving particular tasks, but you're going to need human curation. All right, here's a link. If you go to Delicious at ron/code4lib hierarchy, you'll find about a dozen titles that cover all of this in much greater detail. Thank you very much.